I don't know, I'll try to debug. Okay, so for those who are joining right now, I didn't really say much. We just had a nice bull about where is everybody from, kind of in the area, and then that's pretty much it. We played a song and so on and so forth. So we're going to talk a little bit about administration, and then I'm going to jump into intro to medical imaging and MRI immediately after. So administration-wise, we have a website. And the website, if I click on it, it'll open, but you're not going to see it because I'm not sharing that screen. So I'm just going to switch to that one. And I think you can now see it. And so this is the website that we have. It's right now it's quite crude. It's not filled with a lot of material. But what it has, for example, is useless information like my office address and stuff like this that you probably won't need and things like that. But we have an amazing GSI. Ekin, thank you very much for agreeing to be a GSI in this class. And Ekin is going to be a significant contributor here. Right now, the office hours are not determined, but we'll determine the office hours soon. We have a required text in the class, and that's Dwight Nishimura's Principal Magnetic Resonance Imaging. You can purchase it from lulu.com. It's self-publishing, and it's pretty much printed at cost or very near to cost. So don't buy it from Amazon scammers that go and purchase it and sell it for $100, because you can really get it for $30 or actually less because there's 10% discount right now. It's a great book, and if I can, I'll try to get Dwight, maybe if things open a little bit, to sign your books by the end of the semester. But we'll see. I'll talk to Dwight about it. He might just be able to do that or not. We'll see. There's optional references here, which I highly recommend as well. They're excellent materials to studying MRI. In terms of grading, it's a little bit subject to change, a little bit fluid, but graduate level class and so on and so forth. But there's going to be a weekly assignment that has some potential MATLAB or Python programming. There are 2 wet labs that you would probably not do in person, but you would log into an MRI scanner and basically run the MRI scanner remotely. I think that will be a better solution, a good solution that we found right now. We'll see if things change, and we might do the last lab in person somehow, or at some partial in-person ability. We'll see about that. Now, there's supposed to be 1 midterm towards 2/3 of a semester, and I'm contemplating still about that one. And then definitely a final project that would, I'll talk more about what it is, but it could be kind of a summary of a particular topic, an MRI, an implementation of a paper, having your own idea. It could be, or a literature review on some MRI topic, more advanced MRI topic, or anything that you want to come up with that I'd be happy to talk about. What else? In terms of labs, kind of dry MATLAB Python assignment almost weekly, and then we'll have 2 wet experiments, one on a wrist MRI scanner, and then the other one on a whole body 3T system. Now, all the lecture notes are going to be posted here. I'll try to post them before the lecture, except this time. I'll explain to you why things are a little bit slow this semester, and also, normally my energy level is way higher than this. So I'll explain some of the reasons that it's not so this time. But it has nothing to do with diminishing this. It's not because of the class. All right, assignments are going to be posted here. And we have a Piazza, and then we have Gradescope. That's the way that we're going to communicate. I decided that we don't need B courses. So one less place that we, to look for things. Any questions up to here? Nothing? So clear, huh? Come on. I ordered the book. The book's just gonna arrive in 4 weeks, and you know that kind of stuff. No, no problem. It's not gonna arrive in 4 weeks. It's actually be arriving much earlier than that. So please order the book. All right, and I'll switch to Ekin. Anything you want to add?
No, I guess I already sent the email about the homework, and if anyone has any questions or concerns, just feel free to reach out to me at any point, and I'll determine the office hours soon as well.
Okay, yeah. So this is the required text, and this is Dwight Nishimura. Take a look. One of the nicest, most amazing people I've ever had the pleasure of meeting. It's just I was so lucky to have been able to work with him. And he's standing next to our scanner at UC Berkeley because he came for a visit. So it's a beautiful, beautiful picture. Yeah. All right. Actually, before we jump into this, let me tell you a little bit about myself. So I've been a Cal for about a decade or so. Yeah. Oh my God. Yeah. Actually, 11 years. Yeah. So more than a decade. And yeah. My area of research is medical imaging, in particular MRI. So, you know, most of the research in my group is involving something to do with magnetic resonance. And I've been in the area for almost 20 years, which is, you know, it's not an insignificant amount of time. The reason that there is a class about MRI, and the reason that I'm so super excited to teach is because like they should teach this to like in high school. I mean, they should teach it in kindergarten. This is just such an amazing phenomena, an amazing modality that you know everybody should really know about it. And I'm super excited to tell you about what it is, because it's like every time I teach this, I'm like thinking to myself, no, that cannot be possible. That from this you get that. It's just like not possible, and it is possible, and that's what makes it just so amazing. And so we'll get all to that, and today I'll try to wow you with all sorts of various things. Now, before being at Cal, I actually did my PhD at Stanford in an MRI group, which was amazing. And before that, I actually grew up in Israel, and I did my bachelor degree in Israel in the Technion. So, you know, I came to the US in around 2002, and my English is still not that great. So bear with me. Now, a few things. One of the reasons I'm less enthusiastic is because I'm just like taking all these. I don't know if you can see. No, it's too white. Anyway, lots of painkillers right now. I had a minor injury a couple of weeks ago, and I fractured my leg, and it's been a little bit painful. So first of all, I'm not standing right now. I'm sitting in my living room, and the energy level is a little bit lower. But I'm super happy that I'm able to teach this. And think about it. Let's say it was not in person, probably would have canceled today's class. All right. I'll talk more about when we get to the areas of interest. All right, so medical imaging, folks. This is medical imaging circa 1632. Okay, this is a picture by Rembrandt, famous Dutch painter, and it's in the Mauritshuis Museum in The Hague. And this is me actually visiting that picture, which is it's just amazing picture, just from the lighting and everything. But pretty much this describes medical imaging. I mean, the only way that you could actually go and see inside the body is to go and take a knife and cut the body And then you're able to see what's underneath the skin. Otherwise, there's just no other way. I mean, what can you do? How can you look? I mean, and that it used to be actually a thing where they would take a convict, usually the one that was executed, and once a year they would go and do this anatomy class, and where they show this anatomy in front of people, and that was like a big event. People would pay to come watch, and a physician would go and kind of illustrate and would show parts of the body. Usually they would actually open the chest and abdomen because those actually go bad the earliest, and then afterward they do the rest. So it's pretty interesting. And this was commissioned to Rembrandt by Dr. Nicholas Tulp, who's on the right. This is the doctor. He paid probably the most, and then all the other folks paid also to be part of the picture. So yeah, pretty cool one. And then you can see the cadaver here where they opening their and showing the muscles of the hand and stuff. So pretty exciting, and that's really the only way that you could do this till 1895 or so. And something happened in 1895. What happened? What?
Is it X-rays?
Something. Yeah. X-ray was discovered, right? X-ray was discovered by Roentgen, and this is actually considered the first X-ray image of Roentgen's wife. This is an image from 1895. It's pretty incredible. You could see the bones. You could see the ring she was wearing. It's quite an amazing result. And so since then, really, diagnostic, like medical imaging has pretty much started. Before that, there was no medical imaging. There was maybe cut somebody and then somebody paint a picture, of what's inside. But that's pretty much it. And after that, it's the first time you're able to actually see inside the human body, albeit not in the best way because X-ray have limitations, but you're able to see inside without opening, and that really revolutionized diagnostic medicine. And with medical imaging, you can see internal anatomy like bones and stuff, but you can also visual function of the body in different ways. There are many modalities to use, and I will go over some of them, and many sources of contrast that create variations. But everything here surrounds the concept of an image. So we take the signals that those devices spit out and we place them as intensities in an image that we can visualize. And we as humans are very visual, I guess, animals. We respond a lot to visual information. And this is why, medical imaging has had such a profound impact. So here's kind of the basic concept of a medical imaging system, right? Like you have some body so that you want to image, and there's some energy source, and that energy source depends what it is on the type of modality. It could be sound, it could be magnetic, it could be electromagnetic, it could be optical. That interacts with the body somehow, and then there's a detection of energy that could be the same type of energy, but it could be another type of energy. And then you've got the system that kind of manages it all. It kind of controls how the energy source puts out the energy and how it's collected and how this data is processed, and if you need to do some control or moving things and so on and so forth. And pretty much this is a huge engineering system. It's all about really engineering a system that exploits a physical phenomena in order to create this images of what we're, the underlying physics that we're trying to view. And this is a very general concept. Okay, so if we think of a medical imaging system, what would be requirements for those systems? Any ideas? Like what would we like to have? Oh, yeah, give me some of your like shopping list. Do you have a shopping list for a medical imaging system?
I feel like it should be safe for the person that you're imaging.
That's a good one. But that's always relative, by the way, right? It's safe with respect to what, right? Because we have imaging modalities that are, you put some toxic material inside of you, could cause cancer, but that's probably outweighs, right, the maybe the need to detect cancer and stuff like that. So yes, safety is important, but safety is sometimes relative. What else? Even more basic.
Resolution and contrast.
Contrast, right? So contrast. So some difference that we could see in the image pixel of the anatomy or whatever we want to look for, right? So and there we'd like two things. We'd like specificity and sensitivity, right? Like we want to be sensitive to certain phenomena, but we also want to be specific. So that if we detect something, we would like to say, it is this phenomena with that amount of confidence as opposed to being something else. Okay, what else? You said resolution. Yeah, we want probably high spatial resolution because it's an image, but sometimes we'd also like some other resolution.
Temporal resolution?
What did you say?
Temporal resolution?
Yeah, temporal resolution, right? Yeah, because if we want to be able to image dynamics or things have changed over time. Yeah, so let's see. We want diagnostic contrast. We want, again, specificity and sensitivity. High spatial resolution in both temporal and spatial. We want it to be safe. We want it to be fast. Fast is also important because, if you don't want to lie in a scanner for a month and then get an image, right? That it's unacceptable. But it needs to be fast. And the question is like, what is fast and what is fast enough? We sometimes also want to see function. So maybe that's another one. Other things, maybe we want it to be inexpensive, although there's nothing inexpensive about medical images in general. Definitely the interpretation of them, it's quite expensive because we have to pay somebody that has to study for a decade or so, and maybe more, in order to be able to diagnose them. But maybe that is changing too. We want it to be easy to use, right? Like if it's too complicated, there's too many parameters, like it's really hard to operate. That's a problem. So in general, we can't satisfy all of these for a single modality. But there are many modalities, and often if you want to do some diagnostic, you would actually go through several imaging studies in order to determine what the problem is. And often they'll go from the cheapest one to the most expensive one. Right. First, you might get an ultrasound, then or an X-ray, then you might get a CT, and then you might get either a PET CT or an MRI or something like that. Okay. Any questions? All right, so here are some common medical imaging modalities. There's a lot of imaging general modalities, but medical imaging, there's fewer. And those are the common ones that are actually in clinical practice. So projection X-ray is just the regular X-ray and uses electromagnetic at the X-ray frequencies. Computer tomography, it's the same energy. It's the same X-ray, except that it uses it in a different way. And I'll talk about that. Ultrasound, guess what? It uses sound, which is pretty cool that you can make images with sound. I think that is just awesome. And I'll show you some images of that too. Positron emission tomography and single photon emission tomography, these are nuclear medicine type of modalities, and they actually leverage either gamma radiation or actually it's just gamma radiation, but it's gamma radiation at a level of energy that's extremely high for positron emission tomography. That comes from annihilation of a positron with an electron that converts into 2 photons that are high energy photons that can be detected. Or single photon emission tomography, which is just a gamma source. I'll talk briefly about that, but not too much. Optical coherence tomography is a newer imaging modality that can image very high spatial resolution, pretty good temporal resolution, but not very deep. So it's mainly used in the eye or skin. So this is, but it's a pretty cool imaging modality. And then finally, the most amazing of them all, the crown jewel of medical imaging, which is magnetic resonance imaging, which is just unbelievable. And like, if you just, you know, you can have a course that covers 1, 2, 3, 4, 5, 6 in a single class, but there's really maybe 10 classes you should take about MRI. Just the sheer things that you could do with this stuff. Fascinating. And hopefully I'll convince you that is the case. Now, medical imaging is really a multidisciplinary area, and it's pretty much the reason that I got into this area is because I didn't like to commit to a particular area. Like when I started doing my PhD, I didn't really know what I want to do. I was thinking maybe do something in computing, or maybe do something in signal processing and image processing, or I was actually thinking about radar. So I looked at many things, and I wasn't sure. And what I've actually realized after taking a couple of medical imaging classes is that this is the one discipline that you could actually be in the same discipline and do everything in engineering. Like you can, if you're now more leaning towards clinical application, because now you're really into, you want to save, I don't know, kids, or you want to, you know, solve the problem of cancer or stuff like that, right? So, I mean, you could leverage medical imaging for it. If you want to understand biology, if you want to understand chemistry, of course, physics, math, there's tons of math, you know, you can drown in math just related to MRI. So all of this just comes down under medical imaging. So that's a great thing to actually be studying. That also benefits people considerably, and is not often leading to selling ads online. It's the one job that you would actually maybe actually be able to do this job, as opposed to go and, you know, sell ads. Even though some of my best colleagues that were doing this for a while now are selling ads again, but they might come back. We'll see. All right, so let me just show you a few things. A little bit of advances over the years. So as you can see, just projection X-ray. So X-ray is really imaging shadows. I mean, like what you do, I had a flashlight here. Where's my flashlight? Anyway, don't have a flashlight. Oh yeah, there it is. So here's the flashlight. Can you see me? Can you see my face right now? Yeah. So this is a light, and then basically I'm gonna, you know, shine it on my my hand, and then, you know, the light actually goes through the hand, right? And pretty much what you see at the end is a shadow, and you're supposed to see maybe my bones, right? Because, like, you know, it's blocking, probably would block the light, but you don't see my bones. And anybody has an idea what you don't see my bones, as opposed to just seeing glowing red light?
Are the photons attenuated?
Attenuated. Yeah, there is definitely attenuation. I would expect more attenuation from bone, so that therefore maybe I would expect a shadow. So it's not just attenuation.
There's more scattering after the bone.
Actually, there's scattering through the tissue. The bone would completely block light, right? Like if you took a chicken bone and you shine like a light, I mean, it's just, yeah. So the tissue in between is really scattering, and there's lots of blood in the tissue. So this is why actually the light comes red. It's because of the blood as opposed to, I mean, I'm shining a white light, it comes out red. All the rest of the colors are absorbed, but the red comes out. So light is really not a good modality in order to do imaging. Sorry to say that, Laura Waller. If anybody is from Laura's group, please tell her I said so. In the next group meeting that you have. And I'll check with her that you said, that you told her. All right. Yeah, the thing is, X-ray is really imaging shadow. So the body is semi-transparent to X-ray, and actually it goes through our tissue, but then it's just being attenuated, and it's attenuated differently at different parts of the tissue. Soft tissue is, very little attenuation, and of course bone is much more attenuating. And so you can see this picture, and this is a picture from 1895, and this one is from like, more recent, right? Like, there's definitely improvements, but I wouldn't say that this is like remarkably better, right? Like and this was taken 2 weeks ago, almost exactly, like at 1:24 p.m., I think, yeah. And what you can see here is that definitely there's something not obvious here in the bone. This is a leg, all right? So it's something is not, maybe not right here, but it's still hard to say, to be honest. And the reason is because everything just like overlays on top of each other, right? It is a projection, it's a shadow, and that's what it is. Now, this is CT. Computed tomography is actually a tomographic scheme, so lots of advances. So this is CT from 1975, and this is CT today. Obviously, significantly improved, right? I mean, wow. You can even see some of the soft tissue here, which is pretty striking. And this is a 3D rendering of a CT of a leg. And now, once you render it, you can kind of see all the fractures that are in the bone, both in the tibia and the fibula. This is a fibula, and this is a tibia. So it's much obvious to see it as opposed to looking at the projection before. All right, let's talk about ultrasound. So ultrasound was actually one of the also earliest imaging modalities. Back as far as 1959, there was these are twins imaging in the in uteri, so you could actually see. And one of the main application actually that ultrasound found is for obstetricians, right? So OBGYN, and of course there's others like cardiac ultrasound, which is called echo, or you can actually look at other organs as well. But the majority, a lot of it is considered right now is considered with associated with OBGYN. And this is well, I wouldn't say today, but it's like this is 2006. These are also twins. So definitely improvement in terms of resolution, in terms of quality. And this is maybe 5 years ago. That is not a medical image. This is just a photo of the same twins in a similar orientation. And that's a more recent one from yesterday. So yeah, these things definitely, when they come out, they grow. This is 13 years after. Pretty amazing, right? I know. Crazy. And now I could even, like then I was able to, hey, put your finger in your mouth. And they're like, okay. And now put your finger in your mouth. It was like, no. So what can you do? All right. So let's talk about projection X-ray. So it is a projection format, really small amount of dose. This is really nothing in terms of, don't worry, if somebody gives you an X-ray, just don't worry about it. It's very, very little amount of radiation. Super fast, super inexpensive. Almost every clinic will have an X-ray machine. It's great. And this is a photo of pneumonia in the lungs. Can you see the pneumonia?
I can see something.
Is that this bright thing here?
That's heart. You can see the
yeah, that's right. That's right. That's the heart. Yeah, that's the heart. Unfortunately, it's like it's X-ray, it's a projection, so everything is overlaid. Like you see the ribs, you could see the heart, and then you could see some of the lungs also. And this is pneumonia over here. So there is some, I guess, accumulation of liquid that causes more X-ray attenuation. But it's not obvious to see. And imagine if that part was actually behind the heart. I mean, it's just impossible to see, right? Like you would need to find like weird angles, maybe that it's possible to, but sometimes it's really difficult. So what you could do is make a few projections. Like you don't have to make one. So here's a leg, lower extremity leg, and first of all, you can only see one bone here, but there's actually two bones over there. This is one bone, and like you actually see the other bone kind of overlaying on top of it. So it's the tibia and the fibula in the leg, but because the orientation is such that the projection here is in this direction, so this bone and this bone, they're kind of overlap, and so you can't really distinguish between them that much. But you can definitely see that there's maybe some anomaly here, right? But I don't see any anomaly up here. So what you could do is kind of rotate the leg or rotate the X-ray with respect to the leg and get it at a different angle. So this is a slightly different, angle. So let me just go like this. You see, cool, huh? So now I've rotated it. Definitely something going on here. This is more bright, and the reason it's more bright is because this is, again, the fibula is just behind the tibia. So this is basically the other bone that's kind of slowly showing up. So if I rotate again, oh, now it's showing up. Okay, so this is how we went through, right? So you can kind of start seeing the anatomy. And now you can see there's a fracture here, and now there's another fracture here in the fibula. But of course, all the muscles still overlaps and so on and so forth, right? You can keep going. And as you go more, you can kind of, oh, this is a better angle. Oh, I can see here, this is actually coming out. This is much easier. Oh, there's another fracture here. And then as it rotates, you can maybe see a little bit more of what is going on. So obviously, more directions of projection can give you more information to resolve ambiguities and all sorts of these overlapping regions, right? When we look at them. So there's definitely more information. The question is, how much more information there is in these projections. And I don't know if you know the slice projection theorem, which, or the central slice theorem and so on and so forth, that relates to, that is pretty much the basis behind computed tomography, CT, is that you can, from projection, reconstruct basically the slices themselves. Okay, so if you have projections in all directions, and if you have enough projections, then you'll be able to reconstruct the slices. So, and this is called tomography. And so this is an abdominal CT, this is the spleen, this is the liver, for example, adrenal gland. So very nice contrast that you can see, lots of stuff at high resolution. It is tomographic, so you could see slices. It's very fast. It's so fast. Every time I see somebody take a CT scan, I start crying because, like the time that actually takes to get an MR exam is still very, very long. And CT is just like done. You just go in, done. And it's pretty much a push button. Super high res, moderate amount of dose, although modern CTs leverage some nice detectors and signal processing that can actually reduce this. Cost is between 1 to 2 million, depending on the type of CT that you have. But they're pretty widespread. A lot of hospitals and clinics will have a CT scanner. You can buy actually a micro CT scanner pretty inexpensively and have it in your lab to do, imaging of animals and stuff like that. That's not too hard. You can even actually build your own CT if you can. I've seen somebody take, what do you call this? Like a radioactive source from smoke detectors, and then basically built an apparatus and made a CT scanner, like pretty not great one, but like still okay. Got a nice picture of pepper, you know. So it's not too hard to actually do and make. Although modern ones, you know, get more and more sophisticated. Okay, so the idea there is that you have all these projections and somehow you can create those slices. And this is basically pretty much axial slices. Axial is this is the cross section. And this is going from up all the way to down. And what you see, by the way, anybody has an idea what is stop. What is this?
Is that a pant leg? Or
It's a
sticker?
splint.
Skin?
It's a splint. Yeah, it's like the, yeah, it's like
A cast.
what do you call it? It's yeah, it's yeah, I guess it's a cast, but it's like made of fiberglass. It's a fiberglass cast, and so it actually shows up on CT. Of course, when you do projection X-ray, it would always project and interfere, but with CT, it doesn't really matter so much, right? Because you resolve the volume. As we go down, you can kind of see, oh, there's definitely something not right here in the bone. Like it doesn't seem to be connected somehow. You can obviously, from the slices, people, you know, definitely radiologists can see the 3D very easily. But you know, it takes some training, but it's not too hard. And these are sagittal slices, I think going from right to left, and then you can kind of see how they. And the thing is, once you have the, you know, the 3D, you can render it as you like. And so here's the render of, you know, in the middle of the tibia. So you can kind of create something like that, which is much nicer than I guess the projection. Okay, so that's the idea in CT. And of course, you can further process it to do like volume rendering. This is with, you can see the splint here very nicely. And then after that, you could do some further processing to segment, you know, and you know, remove and look, you know, beyond that and see lots of really cool stuff. All right. So this is all about what's called filterback projection. So the idea here is that you have some X-ray source that shines through some object, and you have a detector, and whatever is being shown on the detector is pretty much a shadow of that X-rays of that object. And so as you go around, you know, the shadow changes, and that provides you enough information to take what's called a sinogram, perform what's called a filter back projection, which we'll be covering somewhat in your class, and then reconstruct the slice from this. And there's just enough information there to be able to do that. Now you think if this is magic, then like MRI should be, I don't know, like I probably need to ask my kids for a meme for that. But you know, this is like somebody tells you that you can actually compute the roots of a second order polynomial, you know, quadratic equation. You go like, what, really? I can do that? It's like, you know, 4a plus minus square root, you know, that kind of stuff. Remember? Like somebody told you, I was like, oh my God, that's like amazing, right? And then like MRI is just like, you know, neural nets, you know, you could do that. Like, I don't know, like way more advanced, you know, like in that. We'll get there. This is CT. Open up.
What's really hard is to be standing in the plane of rotation.
This is the gantry rotates. That makes all these projections. But look how fast it's going. And that thing is heavy. And so it needs to be balanced, like to perfection. And I mean, like the patient lies inside, and today they're actually pretty quiet too. And I don't know how they do it, but it's just amazing how fast these things are. All right. That was CT. I gave it more time than I should have. but yeah, it's still pretty cool modality. But not that cool. But pretty cool, but not that cool. But pretty cool still. It is medical imaging, but it's kind of like optics, but high energy one. Yeah. All right. So ultrasound is a different imaging modality. It's pretty amazing too. It's real time. It's like super fast. It's super inexpensive. Today you can actually make handheld devices completely that have all the compute as well as the transducers, and and something that you can hold in your hand, which is just incredible. Has no ionizing radiation. It's not radiation. It's ultrasound energy. Ultrasound energy can actually cause damage too if you're not careful, but not at the level that it's used for imaging. Has many application. When it's used in the heart, it's called echo. When it's used everywhere else, it's called ultrasound. Whatever, but that's what it is. The problem is it has a little bit low contrast. It only sees differences in impedance of acoustic impedance between tissues. So you would get reflections coming back from those. And it doesn't have great penetration, and penetration actually depends on resolution. If you want to get higher resolution, you have to go to higher frequencies, but then you have more attenuation. So it's kind of, there's definitely trade-offs there. But it's widespread, heavily used, super useful to do all sorts of things, which is pretty amazing. And the math is actually quite complex. Nuclear medicine is a functional imaging modality. You don't use nuclear medicine to see structure so much. For that, you just use CT. But if you want to see actually a metabolism in action, or accumulation of certain compounds due to various physiological reasons, then you would use nuclear medicine. For example, in PET, you would go and use radioactive tracers like carbon-11 or some other type of compounds. You can then tag sugar molecules or glucose molecules with this type of compound. And once you inject that into the body, area that have, high usage of glucose would then accumulate more of that. And then if you make a picture of that, then you'd be able to see where function happens. So pretty amazing modality too. Lots of, lots of agents and different ways of using it. It is low resolution, very low resolution. It is mostly limited by amount of radiation. So the radiation is pretty high, so you can't have a lot of photons. And if you can't have a lot of photons, your signal to noise ratio is going to be down, and your resolution as well. Okay, so that's kind of the idea. Pretty expensive too. The detectors are expensive. The accuracy of the system is pretty expensive. The way it works with PET is that you would have the radioactive compound would decay through a positron emission. Positron is like an electron, but with a positive charge, and it's like basically antimatter, and that cannot last in a matter environment, and very quickly it would interact with an electron, and then the electron and the positron will annihilate each other. And what would happen then is, due to preservation of energy as well as momentum, there'll be two very high energy photons that are going to be shot in opposite direction, 180 degrees. And then if you can detect at the same time these single events, then you can say, oh, this came from a single source, and that gives you a line where these where the event could have happened. And if you have actually some timing information too, maybe you can actually bound that even further. So this is kind of how it works. SPECT is based on gamma radiation, and it uses scintillizers, basically, kind of things that prevent gamma rays from they're not coming straight into the camera from hitting the detector. So this is how you can actually focus a particular direction, is you block all the gamma that is not going straight into your detector, but coming from other regions, so that then you can localize. Both are very useful, but their use cases is more to see function. All right, well, I've talked a lot, and I kind of gave you some examples, and now for the next 30 minutes or so, I'm just going to talk about MR, and we're going to continue also on Thursday talking about MR. I usually don't finish this lecture in a single one. So first of all, MRI versus CT. Most people confuse those, right? Like they would look at those machines, it has a tube, it's round, it has a table, it's a CT or it's an MRI. Like it's just like completely agnostic. Like I would ask often in a class, how many people have ever gone and got an MR? And some people would raise their hand, and then I would say, how many people got a CT? And then like you'd see some puzzling eyes because now they're not sure if what they did was a CT or an MR. And then I would ask, like, did it make noises? And I'd go like, maybe, it's like, was it long? Was it short? Then you can actually decipher what it was. Well, so although from the outside, they don't look that different, from the inside, they look completely different. The physics is completely different. And, you've been staring at the slide for, I don't know, how long? Like 30 seconds? A minute? Can somebody correct me?
It's about a minute.
They're both
This is
CTs,
actually,
right?
no, the left one is an MR and the right one is a CT. I just had them reverse, but nobody really paid it, noticed, because they're not that different from the outside. And in fact, if I have Google Photos, I use Google Photos sometimes, and then I love the search part. You search, and then if I search MRI, I get like I get picture of MRIs, like actual MRI image, MR images. And if I search for MRI scanner, I get nothing. I get like MRI MR images. But if I search for CT scanner, I would always see an MR. Like it will come up, because I don't take pictures of CT scanners. I only take pictures of MR scanners. So for Google, they're all the same. Somebody there, needs to work on their algorithm. Obviously, the beautiful machine on the left cannot be, can be distinguished from the ugly machine on the right. Right. So they're very different, and they're different because, CT is really is based on X-ray, right? So ionizing radiation has rapidly moving parts, like you've seen it. It's really not sensitive to soft tissue almost at all, mostly hard tissue. And it's like super easy to operate. What a technician for CT needs to do is like, their degrees of freedom is like, oh, let's just put a little bit more X-ray or less X-ray. I mean, like there's really just one knob. And today with the limitations, really, there's just this button scan. That's it. I mean, like, that's it. There's nothing else, to choose when you're doing CT. It's just as simple as that. MRI is based on magnetism and magnetic fields. There are no moving parts. Nothing is moving in MRI, even though it makes sounds. There is no ionizing radiation. There are sort of radio frequency radiation in the radio frequency regime, but nothing even close to ionizing radiation. It is super sensitive to soft tissue in so many different ways that are just impossible to explain in a single class even. And the last thing is that it's super complicated to operate. I mean, like way more complicated than anything else. And so hopefully you'll be able to operate one, in a simplified way, but like you'll see kind of the challenges in, making the prescription and stuff like that. But there's just so many degrees of freedom to make an image. If anybody asks you, like, you know, I've often asked this question, like, how fast can you take an MR image? And right now, for some of you, this sounds like a reasonable question. But hopefully by the end of this class, or maybe in the middle of it, you would go like, and then the next thing you're going to say is it depends. Like, you could just not give an answer to this question, because it really depends. It depends on what you're interested in, what you're looking at, what the resolution, what the type of contrast that you were interested. All these determine the length that will take you to create an image. And that can vary from 20 milliseconds to 6 minutes. And it really depends what you want to see. And so you'll see that a lot of the answers in this class is going to be it depends. And if you learn that about MR, then you learn a lot, okay? Because it really depends. And there's maybe infinite ways to do the same thing, like in just so many different ways. And the question is then, like, which way is better? And there's really often not a single parameter that it's like there may be one parameter is better than in one technique than the other one, but then there's another parameter that is not. So it's like, it's really hard to even say what is optimal in many cases. And the answer would be then it depends. It depends what at the end gives you the diagnostic that you're interested in. All right, but yeah, let's talk about history. Lots of history in MR. Pretty amazing history, actually, some even Bay Area history. 1946, Felix Bloch from Stanford, Edward Purcell from Harvard independently discovered that phenomena called nuclear magnetic resonance. Got a Nobel Prize for it in 1952. Pretty amazing phenomenon. That was just in basic physics. The fact that there is such a thing called nuclear magnetic resonance. We'll talk more about that later. 1971, Raymond Damadian shows that there are actually some changes in MR parameters of a tissue ex vivo in cancer. And that made people to start thinking about medical NMR applications. Before that, people just use it in chemistry, use it in physics, analyze, look at molecules and analyze their chemical structure and so on and so forth. Didn't even think about imaging, biological samples, but that was the first time that has been done. I'll talk about Damadian in a second. Very interesting fellow. Quite an outsider in the MR research community, and there are probably repercussions for that. 1972, invention of CT by Hounsfield and Cormack. They got Nobel Prize in medicine for that in 1979. So only 7 years after, which is pretty amazing. Why does that has to do with CT, with MR, right? Because I said they're very different. But as it turns out, in 1973, Paul Lauterberg described actually MRI in a similar way mathematically to CT, that there is a way to acquire data that gives you similar mathematics to CT. And he showed that you can collect images that way. And that's the first time people have actually been able to create image or think about how images can be created using magnetic resonance. In 1970s, Peter Mansfield contributed some key ideas like how to select a slice in a slab, so on and so forth. And then 1975, Ernst proposes other key concepts like Fourier imaging somehow. And he got a Nobel Prize for this in chemistry in 91. From 1982, you start having widespread of clinical MRI. That's when the companies started putting money into see, oh, there's going to be huge money there. They're going to put the investment and create commercial scanners. And that's 1982. So, I mean, for some of you, it feels long, but for me, it doesn't feel long because I remember 1982 pretty well. So, yeah. Anyway, only in 2003, Lauterberg and Mansfield received the Nobel Prize in Medicine for their contribution. And the reason probably was that because Lauterberg was getting very sick and they couldn't, I think, delay the giving the Nobel Prize anymore because he actually died of just maybe a year or two after. But then Damadian didn't get the Nobel Prize, and that was very controversial. Definitely from Damadian's point of view. Some other also in the community thought that he might have should have gotten. Some other folks don't think that is the case. But him being an outsider and also probably not a very nice person kind of helped him not get the Nobel Prize. And that's a full page ad in the New York Times that he put that when he didn't get the Nobel Prize. And you can read the story about that and decide yourself. I don't know what would have been the right thing, to be honest. So it's hard for me to say. So history will tell more later, I guess. But this is MRI 1978. This is MRI today. Quite amazing. I mean, look at this. This is a gorgeous, gorgeous, gorgeous picture of the abdomen. I mean, you can see the kidneys, you can see the gallbladder, you can see some parts of the liver here, you can see fat, muscle, spine. It's just to die for. Just beautiful. A little bit more history. This is I stole these from a slide that Paul Bottomley gave in a lecture in 2012. He was working at GE at that time, and then they're working on Highfield, which was 1.5 Tesla scanners. And that was one of the first images that they got. And look at that excitement, like from getting those images. I mean, images before were really, shit, but this one was really holy shit. I mean, this is a really beautiful image, and they were just so excited. That's what he put in the lab notebook, because they're so excited about what is possible with this. And that's the head coil that they used. Let's look at some images. Guess what? These are the exact same brain, exact same slice. How come the images look so different? How come the images look so different? I mean, it's the same slice, same brain. CT, you take a picture, it will look the same no matter what. Like you can take 100 pictures, 1,000 pictures, probably by the 1,000, you start seeing degradation. And by the 1,000,000 one, you're probably, it's probably going to be black because you've burnt that patient. But there's not, you're not going to change the contrast with CT. Here, look, what's white is black, what's black is dark, it's white. It's like it's different. How come? That's what's so amazing. And the way to generate those differences is just timing and applying different, we'll talk about what pulses mean, but just changing the timing of magnetic fields that you apply, changing a little bit the radio frequency that you apply. And it's mostly the timing, though, that you apply them that creates a completely different contrast. And that allows you, of course, to then kind of, separate different type of tissue. I mean, if I showed you this and you see, oh, this is white and this is white and this is white, but, or, actually here it's dark and this is dark and this is dark. I mean, is there anything there or not? I don't know. The fact that I see that it's bright, I know that this is actually cerebrospinal fluid, and so on and so forth. So like the fact, I mean, it's just so many degrees of freedom to create contrast. Who does computer vision here? Anybody does computer vision? All right, one person at least. If I gave you a computer vision task, in order to separate white and gray and white matter from this image over here, I think you need to develop a very sophisticated algorithm in order to do that. But the beauty about MR is that actually I can change the acquisition just that I can emphasize the difference between gray and white matter. And now white matter is the darker one, gray matter is a little bit brighter gray. And now it's almost as easy as putting a threshold. Right, so there's so much you can do in order to make detection and classification better by changing the way that the image is actually being acquired. So many different contrasts. And these are just anatomical contrasts. We also have contrast agents. You can have magnetic contrast agents like gadolinium. Gadolinium is a heavy metal that is often chelated such that it's not toxic, and then injected into the body, and that changes some of the parameters of the water around it. And here it's an image without a contrast agent, but here with a contrast agent. And because there's a tumor here, the tumor causes leak in the blood barrier, and that leak here leaks blood that has the contrast agent, and that's why we can see the brightening, where we can't see it here so much, even though we see that there is definitely something not right. Okay, so there's definitely lots of types of contrast agents as well. It's just other examples of the abdominal blood vessels on the left. This is a knee image on the right. Look at how much, information you can capture just from those images about what's inside. Just mesmerizing. Here's a beautiful one. On the left is an MR image of the wrist. And there's so many bones on the wrist, right? Like it's so complex. And of course, there's the, I'm losing the words here, between the bones, cartilage, between the bones. That's a little bit darker. There's muscle over here and so on and so forth. There's a problem actually here that you can't see in this image, because this image has signal both from water tissue, but also from fatty tissue. And there's enough fatty tissue in the bone, or actually the bone is mostly made out of fat. The inside of the bone is, has a lot of fat in it. And so that obscure actually the edema that there is in that bone. As it turns out, fat has a slightly different properties that can be actually used such that you can separate the signal from fat and water, or suppress the signal from fat. And if you do that, suddenly, first of all, everything in the bone become dark, right? Like now the bones become dark because there's no signal from fat. But no, those bones, they look bright because there's actually accumulation of fluid because of edema in those bones, and there's injury, and you are able to see it. So yes, if you wanted to do some detection algorithm to see if there's something here, it's going to be very subtle, but it's very easy to, by changing the way you collect the data, if you actually do fat saturation or fat suppression, you're able to see stuff better. Anybody has an idea what is this thing here?
Is that like a tone? Like a noise tone or something?
Yeah, it's some leakage. It's RF leakage into the basically the MR machines are usually have a Faraday cage around them, but if there's some leakage of some tone frequencies, that can actually look like this as an image. And just by knowing Fourier theory, you can actually figure out what frequency that is, and what kind of stuff is, and why it should actually create this type of artifact. And I'll give you a homework about it. How about that at some point? So you're going to actually derive why a tone would actually result in such a thing. This is dynamic contrast enhancement. You can inject contrast and like image fast, if possible. There's a lot of signal processing going on here. And you be able to see dynamics of that contrast agent. And let me just take a look at the left image, and I want you to look at this area, and I'm going to play the video, okay? And what happens is that the subject is being injected in a venous injection with a contrast agent that goes to the heart, then the lungs, then the heart, then the body, and then the arteries basically, and from the arteries then it will go into the veins and then into the tissue. Okay, so take a look what's going around here. Okay, I'm going to play the video. So there's it's very subtle. Let me show you again. Okay, so this is pre-contrast. This is after contrast. So, the kidneys actually absorb a lot of contrast. The rest of the, some of the contrast leaked into the tissue. So the liver is brightened up. You can see the veins over here, a lot of the veins. In the beginning, actually, the signal just goes through the arteries. So this is the aorta. So that's the first thing that becomes bright. And then look what happens. This thing pops out. This is actually a tumor. And that tumor has its own blood supply. And so its MRI parameters are such that it's indistinguishable from the rest of the tissue before contrast. But it absorbs contrast first. So then you could see it. But then after that, it looks like the same as the rest of the tissue. So timing here is a critical thing too. Like when you make the image and like, can you image the dynamics and so on and so forth in order to be able to diagnose this particular tumor. Yeah, MRI can be used also for cardiac, either gated. Gated means that you collect data over many, many cardiac cycles, perhaps breath held, perhaps not. Or you can do real time. This is a real time heart of yours truly. Look, strong heart. But obviously the resolution is going to be limited. The SNR is going to be limited and so on and so forth. Lots more artifacts. Or you could, here it's called Cine. In Cine, it's pretty much kind of stroboscopic imaging. Like you image, you collect data at certain parts of the cardiac cycle and then kind of like assemble such that you can create an image at each part. But like you get partial view every time, but you just over time, you kind of accumulate enough to create an image of an entire single cycle, assuming that all the cycles are exactly the same. Diffusion. Did you know that MRI can be made sensitive to water that are diffusing inside your body? Like water molecules diffuse, right? Like, that's what they do. They diffuse. You can actually make the image sensitive to how much diffusion, and not only how much diffusion, also the orientation of the diffusion. So diffusion is kind of a process where, you have some, water molecule, and then it kind of like travels in a random path, and then, kind of spreads out, right? Well, if you have fiber bundles, like white matter fiber bundles, it's very easy for water to diffuse along the fibers because there's nothing blocking them from just diffusing and moving. But because these fibers are covered by myelin sheath, it's almost impossible for them to cross those sheaths because these myelin sheaths are insulating. And so there cannot be diffusion across the fiber. And so it is possible to make the MR signal sensitive to these orientation, and you can then, from several images with different weighting in different orientation of diffusion, you can create what's called diffusion maps of diffusion anisotropy and fraction. And so here, by color coding each voxel based on the direction of the main diffusion direction, you can create those maps, and you can kind of see that those maps actually, relate to anatomy. So a green is left right, if I'm not mistaken, and then red I think is front back, and then blue I think is top bottom, something like that. I'm not 100% certain, but you can kind of see that there's definitely preferential orientation in those fiber white matter fibers. And then what you could do then is go and do some processing here and kind of try to do what's called fiber tracking and try to see if there is actually, from these direction, try to see if there is something connected to something else, and then create those what's called a fiber tracking algorithm, and kind of try to reproduce the fibers bundles inside the brain and see which areas are connected to. And this is all just from getting MR images. I mean, it is insane. Who would imagine that you could actually see, like, image? I mean, there's no way to image diffusion in vivo. I mean, you can image diffusion by taking, a video in like a transparent fluid where you put like a drop of something and then you see it diffuse. But like inside the body, seeing diffuse, like it's a microscopic scale. How can that even be possible? Turns out it is, and it's actually heavily used. So it's pretty amazing. Oh, did I tell you MRI is sensitive to temperature? Yeah, MRI is sensitive to temperature, and you can actually get quantitative temperature maps like inside the body. What is it used for? Well, it's used for many things, but one of the things it's used for is to do, there's a system which is called MR guided ultrasound, MR guided high intensity focus ultrasound therapy. It's a system in which focus ultrasound is being used to focus high energy ultrasound inside your body, maybe in the brain and so on and so forth, and then ablate tissue. And then they use MR in order to do a closed loop system where they measure the temperature inside the body. They can track which areas are being heated and if they're heated enough, and then guide the ultrasound through the MR. So it's an interesting multimodality cross loop, but that's only because MR is actually sensitive to temperature. We have 4 minutes. So how about I'll just show you the video and maybe we'll end, there. All right, I'll show you this treatment. This is an amazing treatment. Okay, company Insightec that is making those systems. So this is the transducer. That's where you put the head inside. And this is a regular MRI scanner. Okay. This is a patient with essential tremor that is going to go through ablation therapy in order to remove the tremor. Often this is done by putting deep brain stimulators. So it's something invasive that you put some, electrode inside your brain, and then, you stimulate by applying some, frequency. And then after a while, it kind of moves or stops working. So you have to kind of move, retune, maybe wiggle a little bit, to make it work. But it's quite an involved treatment. And this aims to replace that. Using MR, you can do treatment planning. So get the images, do the localization, aim where you want to target the ultrasonic beam. Then you shoot the ultrasound in order to heat the tissue, but in order to see if you're actually on the right spot, they do real-time monitoring of the temperatures using MR, and they apply a lower heat, so subthreshold. So it doesn't actually destroy tissue, but it actually heats it such that it has some effect. And then they can see if there's a reduction in tremor, or if there's maybe damage to the speech or something. Like they want to make sure that if they heat the spot, so the person can still talk, or so on and so forth, and whether that is actually an effective. And then after they do some adjustments, they repeat that a few times, and then they decide, okay, this one, So this one is going to be a therapeutic dose, where they go to 60-something degrees C for a certain amount of time. And then after that, look, this is a real patient. The results are just amazing. So this idea approved for essential tremor. No anesthesia, no incision, no implantable hardware. this is a pretty amazing feat for engineering just to put this thing together, I have to say. Yeah, so I think it's a good time to maybe stop, because what I want to talk about next is,
In this house, we obey the laws of thermodynamics.
The difference between anatomy and function, right? There's the anatomy part where you image the brain, but there's also the function, which part is active and how it's active. And we'll talk more about that on Thursday, and then I'll also tell you how MRI works. Now, what I have to say is that this class, the way it's built, is layered. I'm going to basically cover the entire class on Thursday, but very high level, maybe 100,000 feet. Then I'm going to go and do maybe 1 kilometer. I don't know how many feet it's in 1 kilometer, maybe 3,000. Yeah, 3,000 feet. After that, we're going to do the entire class. And then we're going to go deeper and do it like in, 1 centimeter, right, for the rest. Right, so hopefully, because there's a lot of, interdependent things, so it's better to see some of the big picture stuff. This is also how the book is actually written. And that's why I love using this book, even though it's incomplete. All right, well, thank you so much. And apologize again for the energy level, and hopefully class, I'll try to make it a little bit more interactive as well. And so we'll see what happens. Hope to keep most of you in the class. So if you have some issues and thinking about not taking this for some reason, let me know. But hopefully the homework is not going to break you, but it's really, its aim is to develop a language between us such that you'll talk Fourier and like the same notation, same thing, because otherwise it's going to be difficult. All right. Thanks so much and have a nice evening.
Feel better.
Thank you.